Fractal Frontier means your space for mastering national level exam problems and higher mathematics. I'm your guide for today's deep dive solution. If you are preparing for exams like CSIR NET, GATE, or seeking to strengthen your fundamentals in mathematics, you are in the right place. In today's video, we will tackle a classic problem from the CSIR NET June 2011 mathematical science paper. Our approach will be step by step, which is perfect for both the beginners and advanced learners. Don't forget to join the channel community for more solutions, tips, and exam strategies. The link is in the description. The problem is to check if the given initial value problem exists and is unique. That is, we need to check existence and uniqueness of the given initial value problem. To proceed the given problem, we will use Picard-Lindelof Theorem, which is also called existence and uniqueness theorem. The theorem states that if a function fxy, which is defined on a domain D of R cross R, is continuous with respect to variable x and Lipschitz continuous with respect to the variable y, then the initial value problem dy by dx equal to f of xy subject to the condition yx0 equal to y0 has a unique solution in an interval containing 0. We will recall some facts before approaching to the problem at hand. A polynomial function is everywhere continuous and differentiable. Another fact is a function fxy defined on a bounded domain D is called Lipschitz continuous function with respect to the variable y if the first order partial derivative of f with respect to y is continuous function on domain D. Now the given initial value problem is u dash t is equal to p u of t subject to the condition u0 is equal to 1. So we have then p is a polynomial function of degree n which is greater than equal to 2. Okay, here f of t comma u is equal to p of u. Okay, so since p is a polynomial of degree n, p of u is a polynomial and every polynomial is continuous, so p of u is a continuous and differentiable function. Now del f upon del u, which will be p dash u. So p dash is also a polynomial and it is a polynomial, so p dash u is continuous. So both thus f t comma u is continuous with respect to variable t and its derivative, partial derivative with respect to u is also continuous. By Picard-Lindelof Theorem, the initial value problem u dash t is equal to p of u subject to the condition u01 has a unique solution in an interval containing 0. Okay, so the option 4 is the correct option. So attempt this problem by eliminating options which are not correct. The problem states that p is a polynomial of degree n which is greater than equal to 2. So we can take polynomial as p of u is equal to u square, which is a polynomial of degree exactly 2. The given initial value problem reduces to du by dt is equal to u square subject to the initial condition u0 is equal to 1. Let's solve this problem. So by separation of variables, we can separate each the variable, that is u and t. We will get du by u square equal to dt. Now integrating both the sides, okay, the integration of 1 upon u square will be minus 1 by u, and integration of t will be t plus a constant, let's say a. The given condition is u0 is equal to 1. Okay, therefore by substituting the value of t is 0 and u is equal to 1, we will get minus 1 equal to 0 plus a. So a will be minus 1. We will plug this a in this equation. Therefore minus 1 upon u is equal to t minus 1. So by rearranging the term, 1 upon u is equal to 1 minus t. Therefore the solution of the equation will be ut is equal to 1 upon 1 minus t. So this is the solution when the function is u squared. Okay, so we can see that this factor will be 0 when t is equal to 1. The solution exists only when t is not equal to 1. Therefore solution exists when t is not equal to 1. Okay, so we have calculated the solution ut is equal to 1 minus t, which is unique solution. Okay, and it exists when t is not 1. So first option, a unique solution is incorrect, because solution does not exist when t is equal to 1. N number of distinct solution? No, there is only one solution. No solution in any interval containing 0. There is indeed a solution which is ut equal to 1 upon 1 minus t. So there exists solution, so 3 will not be an option. Hence option 4 is correct. Okay, and the proof that option 4 is correct we have provided earlier.
So first we will briefly explore about the interval of existence, means how to calculate the interval of existence for a given initial value problem. So we consider the initial value problem dy by dx equal to f of xy subject to the condition yx0 equal to y0. It is a given initial value problem where we assume that fxy is continuous in a closed domain D, where domain D is defined as all the points in domain R square such that x minus x0 less than equal to a and y minus y0 less than equal to b. It is a closed domain where function f of xy is continuous. It is assumed that a and b both are positive. Since f is continuous in a closed domain, so it will be bounded on the domain D. So we assume that the mod of fxy is less than equal to m. So m is the bound of the function fxy for the domain D. Now we define h equal to minimum of a b by m. Then the maximum interval of existence is given by mod x minus x naught less than equal to h. So what is the information? Why we need this information? So if a differential equation is given of the type dy by dx equal to f of xy and a condition is given yx0 equal to y0, then how to find the maximal interval of existence? So first we have to define the domain D. Sometimes the domain is given in the problem. Then we have to find the maximum bound f of xy mod less than m. So we have to find the value of m, then we will define h such that it is minimum of both the a and b by m. When we find the value of h, we can easily determine the maximal interval of existence such that x minus x0 less than equal to h. So let's discuss the problem asked in CSIR NET June 2011. The problem is, for the initial value problem dy by dx equal to y square plus cos square x, where x is greater than 0 and y0 equal to 0. The largest interval of existence of the solution predicted by Picard theorem is. So we have to find the largest interval of existence for the initial value problem. These are the options. So first we will find the bound m and then we will calculate the value of h. So the given initial value problem is this, subject to the condition y0 equal to 0. Here when we compare it with dy by dx equal to f of xy, this is our f of xy. So f of xy equal to y square plus cos square x, and here domain is not given, so we will assume here x0 value is 0 and y0 value is 0. So the domain we can define as d equal to xy belongs to r square such that x minus x0 is 0 less than equal to a and y minus 0 less than equal to b. So fxy is continuous on the closed interval because it composed by two functions. One is polynomial function and one is trigonometric function which is continuous. Now we will calculate the value of mod fxy. So it will be mod y square plus cos square x. By using triangular inequality, we can write it as less than equal to mod y square. It will be less than equal to mod y square plus mod cos square x, and we can write it as mod y square plus mod cos square x. Since cos x lies between minus 1 to 1, so cos square x is less than equal to 1. So we can write it as this will be 1, and in the domain y is less than equal to b, so we can replace its upper bound b. So mod f of xy is less than equal to b square plus 1. So we will take this as the value of m. Now we define h equal to minimum a b by m. By placing the value of m, we will get minimum a b divided by a square plus b square plus 1. So how to find the minimum value? So we will use the concept of maxima and minima from differential calculus. So we assume this as a function of b. Okay. For the minimal value of fb, we have the necessary condition as the first derivative with respect to b must be 0. So we will calculate the first derivative. So it will be the first derivative of fb and its value will be 1 minus b square divided by b square plus 1 ka whole square equal to 0. Since b is a real number, so b square plus 1 will not be 0. So we can write it as 1 minus b square equal to 0. So we will get b square equal to 1 or b equal to plus minus 1. Since it is assumed that b is greater than 0, so b will be 1. So we have find the value of b such that fb is minimum. Obviously we have to check the condition for minima, which is the second order derivative. F double dash b must be greater than 0. We can check it and it will be greater than 0. So the value of h will be minimum a we replace the value of b as 1, so it will be 1 upon 1 square plus 1, that is 1 by 2. So since a is not given, we can choose the value of h as 1 by 2. So the maximum interval of existence will be mod x minus x0, where x0 value is 0. So mod x minus 0 less than equal to h, and by substituting the value of h as 1 by 2, we will get mod x is less than equal to 1 by 2. So x will be in 0 to 1 by 2 because x is already given as greater than 0. So the maximum existence interval will be closed interval 0 to 1 by 2. So option B will be the correct option. So this will be the correct option. Equations. Let's look at the question on the screen. It's dy upon dx equal to 60 y square raised to the power 1 by 5 where x is greater than 0 and the initial condition is y0 equal to 0. And we are asked how many solutions does this differential equation have. In the given problem, if we compare the given problem by dy upon dx equal to f of xy, then f of xy is 60 y square raised to the power 1 by 5, or we can say 60 y raised to the power 2 by 5. So we can see that fxy is continuous around the origin, that is x0 comma y0. Now if we calculate the partial derivative with respect to y, so del f upon del y equal to 60 into 2 raised to the power 5 minus 1 and minus 3 by 5. So we can see that del f upon del y is not bounded around 0 comma 0. So f is not Lipschitz continuous. So here fxy is continuous but not Lipschitz continuous around 0 comma 0. So here Picard's existence theorem is applicable, which means that the given initial value problem has at least one solution, but uniqueness condition fail. So the given initial value problem has a solution but not unique. So we can say that the given initial value problem has infinitely many solutions. Now we will discuss what can be the possible solution of the given initial value problem. For this, we take a general differential equation of the type dy upon dx equal to k y raised to the power alpha, where alpha is a constant real value between 0 and 1. And the condition is ya equal to 0, where a is any fixed real constant. So we can see that yx equal to 0 is a solution which is trivial solution because it satisfies the differential equation as well as the boundary initial condition. Now we will solve this differential equation by the method of separation of variables and then derive the solution. So dy upon dx equal to k y raised to the power alpha. By separating the variable y and x, we will get dy by y raised to the power alpha equal to k dx. On integration, it will be y raised to the power minus alpha plus 1 divided by minus alpha plus 1. We have alpha lies between 0 and 1. It is not equal to 1, so 1 minus alpha is not 0. So y raised to the power 1 minus alpha will be 1 minus alpha into kx plus constant c. By taking the power 1 upon 1 minus alpha, yx will be this. So there are these constant value. We will replace this by constant beta and this by constant gamma. So we have yx equal to beta kx plus c raised to the power gamma. The given initial condition is ya equal to 0. So we will get beta ka plus c raised to the power gamma equal to 0. So c will be minus ak. By substituting into this, we will get yx equal to beta kx minus ak raised to the power gamma. It will be a beta k raised to the power gamma x minus e raised to the power gamma. So this constant beta into k raised to the power gamma we will take as a new constant beta dash. So the solution will be yx equal to beta dash x minus e raised to the power gamma is the solution of the given initial value problem for alpha belongs to 0, 1, where beta dash equal to beta k raised to the power gamma. So we have seen that there are two solutions, yx equal to 0 and non-trivial solution yx equal to beta dash or some other constant x minus e raised to the power gamma. Okay, where beta dash and gamma are determined by the k and alpha. Now we will see some other solution. So for any constant parameter greater than equal to a, we will define ycx a family of solution such that for x less than equal to c, the solution is 0. When x greater than equal to c, the solution is beta dash x minus c raised to the power gamma. It is derived by this solution. So we can see that dyc by dx equal to k y raised to the power alpha, and it will satisfy the condition y equal to 0. So it is also a solution to the given initial value problem. So we can conclude that the initial value problem dy upon dx equal to k y raised to the power alpha when alpha belongs to 0 to 1 subject to the condition y equal to 0 has infinitely many solutions. There is one point that how this solution satisfy the condition y equal to 0, because we already taken the parameter c as c greater than equal to a, and when we take yca, it means the solution evaluated at x equal to a, which is less than equal to c, or when x less than equal to c, the solution is 0. Hence it satisfies the initial condition. So we can apply this result for our problem asked in CSIR NET December 2012. So here the constant k is given as 60. It doesn't matter. All we need to examine is the value of alpha. So here alpha is 2 by 5, which falls in between 0 and 1. So by this result we can say that the given initial value problem has infinitely many solutions. You just need to verify also that ya must be 0. So the value of y at initial point must be 0. So next time you see a differential equation like this, don't rush to integrate, just check the value of alpha. If alpha lies between 0 and 1 and y at x0 equal to 0, then the differential equation or the initial value problem has infinite number of solutions. From the CSIR NET Mathematics June 2013 paper, this problem perfectly demonstrates what happens when the Lipschitz condition fails. That is, the existence remains but uniqueness is lost. Let's begin by recalling Peano's existence theorem, which lies at the heart of this concept. Peano's existence theorem states that if the function f of xy is continuous in a neighborhood around the point x0, y0, then the initial value problem dy over dx equal to f of xy subject to the initial condition yx0 equal to y0 has at least one solution in some interval around x0. The theorem does not guarantee uniqueness, it only ensures that a solution exists. To guarantee uniqueness, we need a stronger condition, which is the Lipschitz continuity as given by the Picard-Lindelof Theorem. Here f of xy is x y raised to the power 1 by 3. So here f of xy equal to x y raised to the power 1 by 3, which is continuous function around x0 y0. Therefore by Peano theorem, the initial value problem dy upon dx equal to x, y raised to the power 1 by 3 subject to the condition y0 equal to 0 has at least one solution. Okay. Now we will check if the function f of xy satisfies the Lipschitz continuity or not. So for this we will calculate the derivative of f with respect to the variable y, which is 1 by 3 x y raised to the power minus 2 by 3. Okay, is not bounded in the neighborhood of 0, 0. Therefore, the function f of y equal to x y raised to the power 1 by 3 is not Lipschitz continuous function with respect to variable y. Okay, so now we will analyze the option. So first option, the function does not satisfy a Lipschitz condition with respect to y in any neighborhood of y equal to 0, which is a correct option. The second option is there exists a unique solution for the initial value problem. Since we have that f of xy does not satisfy a Lipschitz condition with respect to the variable y, so we cannot say that the given initial value problem has a unique solution or not, but it indeed has at least one solution. So option number 3 is not correct. The given initial value problem is dy over dx equal to x y raised to the power 1 by 3 subject to the condition y0 equal to 0. So we will use separation of variable method to solve the initial value problem. By separating the variable x and y, we get dy over y raised to the power 1 by 3 equal to x dx. On integration, we get y raised to the power 2 by 3 upon 2 by 3 equal to x square by 2 plus an integration constant a. Since y0 equal to 0, we will get the constant as 0. Therefore, the solution of the initial value problem is y raised to the power 2 by 3 equal to x square upon 3. Also, yx equal to 0, that is the trivial solution, is also solution of the given initial value problem. So we have two solutions. One solution is y raised to the power 2 by 3 equal to x square upon 3, and other solution is yx equal to 0. So the option 2, there exists a unique solution, is not correct, but there exists more than one solution for the initial value problem is correct option. Hence option 1 and 4 are the correct option for the given problem. That for any alpha greater than equal to 0, yx defined by this, that is for mod x less than equal to alpha, we define yx as 0, and for mod x greater than alpha, we define yx equal to plus minus x square minus e square divided by 3 raised to the power 3 by 2 is also a solution to the given initial value problem. So we can say that for each alpha there exists a solution, therefore the given initial value problem has infinitely many solutions. So in summary, if fxy is continuous, then the initial value problem has at least one solution, that is the continuity of fxy guarantees the existence of the given initial value problem. If we add one more condition, that is fxy is Lipschitz continuous with respect to variable y, then the initial value problem has a unique solution, that is Continuity plus Lipschitz continuity with respect to variable y guarantees the existence and uniqueness of the given initial value problem. This theorem is the first one is called Peano's theorem and second one is called Picard-Lindelof theorem. Now let's discuss some other problem. This is problem asked in CSIR NET June 2013. So the problem is, consider the initial value problem dy by dx equal to y square subject to the initial condition y0 equal to 1 where xy belongs to r cross r. Then there exists a unique solution of the initial value problem on. So we have to find the interval. But there is one problem. In Picard's theorem, we have assumed that the xy belongs to a bounded closed domain D. Okay, but here xy belongs to the whole Euclidean plane R square. So the domain is not closed, not bounded. So we cannot apply the Picard's theorem. To find the interval here, we will first solve the differential equation with the initial condition, then analyze the option. So let's start. The given differential equation is dy by dx equal to y square, which is a first order differential equation and it is separable in x and y. So we will separate the variables. So dy by y square equal to dx. By integrating, it will be integration 1 upon y square dy equal to integration dx. So the integral of 1 upon y square is minus 1 upon y and integral of x is x, and c is a constant of integration which needs to be determined. The given condition is y is 0 equal to 1, that is at x equal to 0 y is 1. If we put here y equal to 1 and x equal to 0, we will get c equal to minus 1. So a solution to the given initial value problem is minus 1 upon y equal to x, and by taking c equal to minus 1, we will get y equal to 1 minus x. This solution blows up when x not equal to x equal to 1. So for the existence of solution, we must have that x is not equal to 1. Now we analyze the option. The first option is minus infinity to infinity. Since 1 belongs to that interval, so this option is not correct. Option C is minus 2 to 2. Since 1 belongs to that interval, so this will also be incorrect. Similarly, option D is incorrect. Now, in option B, the interval is given as 1 to infinity. Since 1 does not belongs to that interval, so it is open from n. 1 is not member of this open interval. Therefore, option B is the correct option. Similarly, we can find interval for other problems when the interval is not bounded. The domain D is not bounded. So in that case, we will find the solution of the differential equation, use that given initial conditions, and then analyze the solution yx. And based on the solution, we will decide which option is correct or which are not.
The problem is, let ut be a continuously differentiable function taking non-negative values for t greater than 0. The value of t is greater than 0 and satisfy the differential equation u dash t equal to 3 ut raised to the power 2 by 3, and the initial condition is u0 equal to 0. Which of the following are possible solutions of the above equation? So we have to choose all the correct solutions. So let's begin. So similar to the previous problem, we first derive a solution by the method of separation of variable. So this is the given differential equation. We can write it as du by dt equal to 3 u raised to the power 2 by 3. Now separate the variable u and t. We will get du by 3 u raised to the power 2 by 3 equal to dt. On integration, it will be integration equal to t plus a, where a is a constant which will be determined by the given initial condition. On integration, we will get this, and so u raised to the power 1 by 3 equal to t plus a. It is given that at t equal to 0, u equal to 0. Therefore, a must be 0. We will get u raised to the power 1 by 3 equal to t. So ut will be t raised to the power 3. So we can see that ut equal to 0, which is a trivial solution because it satisfies both the differential equation and initial condition. Ut equal to t cube, which we have derived by using the method of separation of variable. So in general, for c greater than equal to 0, uct equal to 0 when t is less than c and t minus c raised to the power 3. We have used this solution to generalize this in the form of t minus c raised to the power 3. So this will be a solution to the given initial value problem. So if we see the given problem, here c is 1 and c is 3. So we can put first c equal to 1, which is greater than 0. So for c equal to 1, when t is in between 0 and 1, the solution is 0. When t greater than equal to 1, solution will be t minus 1 raised to the power 3, which is a solution to the given initial value problem. Similarly, if we take c equal to 3, then ut equal to this, which is also a solution. Hence, all the 4 options are correct. So now we will see a similar problem. So there is another problem which is asked in December 2015 paper. It is given that ut, a continuously differentiable function taking non-negative values for t greater than 0 and satisfying the initial value problem, u dash t equal to 4 u raised to the power 3 by 4 with the condition u0 equal to 0. Then we have to check what can be the possible values of solution ut. So here ut equal to 0 will be trivial solution. If we calculate it, the solution du by dt equal to 4 u raised to the power 3 by 4 by the method of separation of variable. Let's see what will be the solution. So on integration, it will be a is constant, it will be u raised to the power 1 by 4 equal to t plus a. If we put u0 equal to 0, then we will get equal to 0. So u raised to the power 1 by 4 equal to t, or we can see that ut will be t raised to the power 4. So by inspecting the options, ut equal to 0 will be the trivial solution, ut equal to t raised to the power 4, which is a solution by the method of separation of variable, and we can extend this solution for any c greater than equal to 0 by branching it out for t 0 to c and t minus c raised to the power 4 t greater than equal to c. If we put c equal to 1, we will get third option. If we put c equal to 10, we will get fourth option. Hence all the 4 options are correct. So these are some very easy problems asked in multiple selective questions of 4.75 marks. So by using this method, we can obtain general solution y is equal to this. We just have to keep in mind this kind of equation, dy by dx equal to k y raised to the power alpha, where alpha is in between 0 and 1, where condition is given y equal to 0, where a is any real constant. So it will have multiple solutions. One is trivial solution yx equal to 0. One we will get by using the method of separation of variable, and by this solution we can extend this solution by replacing this a to any constant c, where c is greater than a. Okay, here in the today's problem a is 0, so we just get solution like x minus 0 raised to the power gamma. We replace it by x minus c raised to the power gamma.
We will look at a problem from the CSIR NET Mathematics December 2014 paper, which illustrates how the Lipschitz condition guarantees uniqueness and restricts the behavior of the solution curve. So the problem is given that y is a differentiable function and satisfy the differential equation dy over dx equal to function of y for all x belongs to the real number r. The initial and boundary condition are y0 equal to 0 and y1 equal to 0, where f is given as a r to r Lipschitz continuous function. Then we have to test which of the following options is or are correct. In this video, we have explained the Picard-Lindelof theorem, which is also called the existence uniqueness theorem, which states that if a function f of xy defined on a domain D of r cross r is continuous with respect to variable x and Lipschitz continuous with respect to variable y, then the initial value problem dy over dx equal to function of xy with the initial condition yx0 equal to y0 has a unique solution in an interval containing x0. In the given problem, f of xy is simply function of y, which is a Lipschitz continuous function. F xy equal to fy is a Lipschitz continuous function. So, by Picard-Lindelof's theorem, the given initial value problem, which is dy over dx equal to fi subject to the condition y0 is equal to 0, has a unique solution. Since we are given that y0 equal to y1 equal to 0, so by Rolle's theorem, there exists C belongs to 0, 1 such that y dash C is equal to 0. Now, from the given initial value problem, y dash x is equal to function of y at x equal to c, y dash c is equal to function of y of that is f of yc is equal to 0. Okay. Now we will assume that the function zx equal to y star, which is equal to y at c, is a constant function. Its derivative with respect to x is 0 and function of z x, that is f of y star, or we can say f of y which is equal to 0. Therefore, zx is a solution to the ordinary differential equation dy upon dx equal to function of y, but the solution is unique. Therefore, zx must be equal to yx. That is, y of c must be equal to y of x. Since y of 0 equal to 0 and y of 1 equal to 0, therefore y of c is equal to 0. Okay. And hence the solution of the given initial value problem is identically 0. So yx is identically 0, which means yx equal to 0 for all values of x. Now we will analyze each option one by one. The first option is yx equal to 0 if and only if x equal to either 0 or x equal to 1, which is not true because yx is anywhere 0. It is identically 0, so this option is incorrect option. Second one is y is bounded, since yx equal to 0 is a constant function. Therefore, y of x is bounded. So it is a correct option. Now the option 1 is saying that y is strictly increasing, which is incorrect because y of x is 0 is a monotonic increasing function, not strictly increasing function. Option number 4 is dy over dx. Since yx is equal to 0 everywhere, so its derivative with respect to x is also 0, is bounded. So the option is dy over dx is unbounded is not correct. Thus, the only correct option is option number 2. Okay, this was the CSIR NET Mathematics December 2014 problem showing how the Lipschitz condition ensure uniqueness. This problem is from CSIR NET June 2016 problem. So the problem is for lambda belongs to R. Consider the differential equation y dash x equal to lambda sine x plus y, where y0 equal to 1. Then this initial value problem has first option, no solution in any neighborhood of 0, a solution in R if lambda mod lambda less than 1, a solution in a neighborhood of 0, a solution in R only if mod lambda greater than 1. So if we compare it with y dash equal to f of xy, then f of xy is lambda sine x plus y. Since it is a trigonometric function, it is continuous everywhere. Now mod del f upon del y, we will partially differentiate f with respect to y, then we will get lambda. The derivative of sine is cos x plus y, which is less than equal to mod lambda for all lambda. The bound does not depend on x or y, so it is globally Lipschitz continuous function with respect to y. Therefore, by Picard-Lindelof theorem, the solution of the initial value problem dy by dx equal to f of xy, y0 equal to 1 has a unique solution in R, that is on the whole real line. Now we will examine the options. No solution is not correct, it has a unique solution. A solution in R if mod lambda. Indeed, this problem has a solution in R for all the values of lambda, so it is correct option. A solution in a neighborhood, it is also correct. A solution in R only if mod lambda greater than 1. This part is correct, but here it is written that only if. It is not true because the given initial value problem has solution for all lambda. Therefore, this option will be incorrect. Hence, option B and C are the correct options. Now we will use our previous discussion to answer CSIR NET December 2016 problem, which states that initial value problem y dash t equal to fyt subject to y0 equal to a belongs to R, where f is a function given defined from R to R. Then we have to examine which option is true and which is not. So first option is there exists a continuous function and a belongs to R such that the above problem does not have a solution in any neighborhood of 0. Second option is the problem has a unique solution for every a belongs to R when f is Lipschitz continuous. Third is when f is twice continuously differentiable, the maximum interval of existence for the above initial value problem is R. The maximal interval of existence for the above problem is R when f is bounded and continuously differentiable. So this is Picard-Lindelof Theorem, which states that if a function f of xy defined on a domain D is continuous with respect to x and Lipschitz continuous with respect to y, then the initial value problem dy by dx subject to the condition yx0 equal to y0 has a unique solution in an interval containing x0. And also the Peano's existence theorem, if the function is continuous in a neighborhood around the point x0, y0, then the initial value problem has at least one solution in some interval around x0. So by Picard-Lindelof theorem, we can guarantee that the solution is unique, and by Peano's theorem, we can just say that the initial value problem has at least one solution. It does not guarantee about the uniqueness. So we can summarize that if f is continuous with respect to x and Lipschitz continuous with respect to y, then solution exists and is unique. And if f is continuous around x0, y0, then solution exists. So by using these two theorems, we will analyze the question. So the first option is if f is a continuous function from R to R, okay, then by Peano's existence theorem, this initial value problem has at least one solution around x0, but the option saying that the problem does not have a solution in any neighborhood of 0, which is not correct. So by Peano's existence theorem, there will exist a solution. So this option is not true. You can mark it. Okay. In second option, it is given that when f is Lipschitz continuous, then the problem has a unique solution for every a belongs to R. So by Picard-Lindelof theorem, if f is Lipschitz continuous, that means it will continuous as well as Lipschitz continuous, then it will have a unique solution. So option 2 is a correct option. For option C, we will provide a counter example because the option is saying that when f is twice continuously differentiable function, the maximum interval is R. So it is not necessary that maximum interval is R. Sometimes there may be some breakdown point alpha or some other points where solution tends to infinity. So it will not be the whole real number. So for this we will take an example. Consider the differential equation dy by dx equal to y square. Subject to the condition y0 equal to a, then its solution we can check that yx will be a upon 1 minus ax. So the condition is x will not be equal to 1 by. So the maximal interval is not R. The maximal interval of existence is not the whole real number because the solution breaks down at x equal to 1 by a, which is a part of the real number. So the maximal interval will not be whole R. So C is not correct option. So this option 3 is not correct. So let's talk about option number 4. So option number 4. If f is bounded and continuously differentiable on R, then f is globally Lipschitz function. Therefore, the solution will exist globally, that is, the maximum interval of existence is R. So the fourth option will be correct. So when will be the maximal interval of existence equal to the whole real line? When f is bounded and continuously differentiable. So the option 4 is correct. And in conclusion, the option 2 and 4 are correct option, 1 and 3 are incorrect option. Next problem is from CSIR NET June 2017. The problem is, if the solution to the initial value problem dy by dx equal to y square plus x square subject to the condition y0 equal to 2 where x is greater than 0 exists in the interval 0 to L0 and the maximal interval of existence for the initial value problem dz by dx equal to z square subject to the condition z0 equal to 1 where x is greater than 0 is 0 to L1, then which of the following statements are correct? So basically there are two initial value problem and their interval of existence are given. It's 0 to L0 and 0 to L1. So we have to find the value of L0 and L1. So let's do it. The first initial value problem is dy by dx equal to y square plus x square subject to the condition y0 equal to 2. We assume fxy as y square plus x square, which is a continuous function on the all real numbers. Now there is a comparison theorem for differential equations which states that if y dash x equal to fxy and u dash x equal to g of u with the condition that fxy greater than equal to gy and y0 equal to u0. If these are the conditions, then yx greater than equal to ux for all x in the common interval. So we will use this comparison theorem to find the value of L0 because by direct method we cannot find the value of L0. The domain D is not explicitly given, it is only given that x is greater than 0, that is it is unbounded domain, so we cannot make any conclusion based on the basis of this. So we will use this comparison theorem. It is very important theorem for this question. So we have fxy equal to x square plus y square and for x greater than equal to 0, this is always greater than equal to y square. So we will consider the initial value problem. In comparison theorem, we consider a secondary initial value problem u dash x equal to g of u. So we will condition, we will use u dash and du by dx equal to u square. Subject to the same condition because the condition on y is given as y0 equal to 2. So we will use the same condition u0 equal to 2. Then fxy, which is x square plus y square, will be greater than gy because we have considered g as u square. So gu is u square. So gy will be y square. Now we will solve the initial value problem du by dx equal to u square. So we will separate the variable on integration. It will give 1 upon u with minus sign equal to x plus c. Since the initial condition is u0 equal to 2, the value of constant will be minus 1 by 2. So minus 1 upon u equal to x minus half, and the solution of the initial value problem u dash equal to v of u equal to u square subject to u0 equal to 2 will be 2 upon 1 minus 2x, where x is not equal to 1 by 2. When x tends to 1 by 2, the solution will tend to infinity. So the maximum interval for the initial value problem du by dx equal to u square, u0 equal to 2 is 0 to 1 by 2. And by comparison theorem, yx will be greater than equal to ux. But since ux tends to infinity and x tends to 1 by 2, it means yx cannot exist past x equal to 1 by 2. Therefore, L0 must be less than equal to 1 by 2. Now we will analyze the second initial value problem dz by dx equal to z square subject to z0 equal to 1. By using the method of separation of variables, the solution will be z equal to 1 upon 1 minus x when x not equal to 1. So the maximal interval of existence will be 0 to 1. Therefore, L1 equal to 1. So by analyzing both the initial value problems, we got L1, so L0 less than equal to 1 by 2 and L1 equal to 1. Now we will check each options. In first option, L1 equal to 1 is correct, but L0 is less than 1 by 2, not greater than 1. So this option is not correct. Second option is correct because L1 is 1, okay, but L0 is less than equal to 1 by 2 is also less than equal to 1, because so option B is correct. Option D, L1 equal to 1, which is also less than 2, so it is also correct option. And the last option is L1 greater than 2, which is not correct because L1 is 1, which is not greater than 2. So option 2 and 3 are the correct option for this problem. So
Initial value problem is given as dy by dx equal to y square plus x square subject to the condition y0 equal to 1. Let's assume that fxy equal to y square plus x square, which is a continuous function because it's a polynomial function. So this is the comparison theorem. If y dash x equal to fxy and u dash x equal to gu with this condition for all x, then yx greater than equal to ux. So we will use this comparison theorem. For more detail, check out the previous video. Here fxy equal to x square plus y square, which is greater than equal to y square. For all x greater than equal to 0, we will consider the differential equation du by dx equal to u square. So here g of u is u square, and the condition is the same as the initial value problem given in the question. Y0 equal to 1, we have taken u0 equal to 1. Now we will solve this equation and decide the block behavior of the solution yx. Since here x square plus y square is fxy, so fxy is greater than equal to g of y, where g of u is assumed as u square. Now consider the differential equation du by dx equal to u square. By using the method of separation of variable, we will arrive at minus 1 upon u equal to x plus c, where c is constant of integration. The condition is u0 equal to 1. By using that condition, we will get c equal to minus 1. So the solution is ux equal to 1 upon 1 minus x. So the solution blow up at x equal to 1. So the maximal interval for du by dx equal to u square subject to the condition u0 equal to 1 is 0 to 1, where 1 is not included. And by comparison theorem, yx greater than equal to ux and ux tends to infinity as x tends to 1. Therefore, yx cannot exist past 1. Therefore, we can conclude that since the function f of xy equal to x square plus y square is a Lipschitz function, so there exists a unique solution, okay, about x equal to 0. So there exists a unique solution is a correct option. As we know, every solution is bounded in 0 to pi by 4. Since we have that the solution blow up past 1, therefore before 1 in interval 0 to 1 the solution will remain bounded. So the solution yx will be bounded in 0 to pi by 4, which is a part of the interval 0 to 1. So the first option is correct, second option is correct, and the third option is the solution exhibits a singularity at some point in 0 to 1. This is also correct because it blow ups at 1, at least 1 or after, so it has singularity in the interval 0 to 1. So this is also a correct option. Third option, last option is the solution becomes unbounded in some subinterval of pi by 4 to 1, which is also true because this interval is a part of close 0 open 1. So this option is also true. Hence, for this problem, which is asked in CSIR NET December 2019 paper, all the 4 options are correct options. Let's discuss another problem from CSIR NET December 2009, which is a second paper held for Assam. So the problem is, let mod fx is less than equal to 4 mod x for x belongs to R, the largest possible value for mod x1 where x dash t equal to f of xt for t greater than 0 and the condition is x0 equal to 3. So we have to find the largest possible value of x1. So to use comparison theorem, we assume the function g of u as 4u. So we consider the initial value problem, du by dt equal to 4u subject to the condition u0 equal to 3. Now we solve it by using the method of separation of variables. We will get the solution log u equal to 4t plus a constant log c. To determine the constant, we will use the condition u0 equal to 3 and we will arrive at c is equal to 3. So the solution will be ut equal to 3 exponential 4t. So by the comparison theorem, xt will be less than equal to u of t. So xt will be less than 3 e raised to the power 4t. We have to find the value of mod x1. So x1 here will be 3 e raised to the power 4. So the maximum possible value for mod x1 is 3 e raised to the power 4. Hence the first option is correct. We can also approach this problem by using Gronwall's inequality. So this is the statement for Gronwall's inequality. If u dash t is less than equal to beta t u of t for t belongs to some interval I, then ut is less than equal to ua exponential integral a to t beta s ds. So in our case, we take ut as mod of xt and a equal to 0. So then by the Gronwall's inequality, UT means x t mod less than equal to u0 exponential integral 0 to t. Here beta is 4 because we are given that mod fx is less than equal to 4 mod x. So ut will be mod x and beta is 4. So by solving it, we get mod xt is less than 3 exponential 4t. We have to find the value of x1, so mod x1 is less than equal to 3 exponential 4. Hence first option is correct option. We can derive a general result for the initial value problem. Dy by dx equal to x square plus y square subject to the condition y0 equal to y0. The largest interval of existence for this initial value problem will be 0 to 1 by y0. So by using this general result, we can solve multiple problems in lesser time. So this is an important result. You can derive it by using the comparison theorem.
December 2019 paper, which is held for Assam region. So the problem is, let z defined from real number r to r be locally Lipschitz, and this condition x into zx is less than equal to 0 for all real numbers. Then which of the following statements are true for the initial value problem x dash t equal to gxt with the condition x0 equal to x0. So these are the four options. There exists a local solution for any x0 belongs to r. The solution exists. There is a finite time blow up for some x0. All the solutions are bounded. So basically we have to check the existence of the solution locally and on the interval 0 to infinity, boundedness of the solution. So let's begin. Since it is given that the function g is locally Lipschitz, so by Picard-Lindelof Theorem, we can say that the initial value problem dx by dt equal to gx subject to the condition has a unique solution around x0. So it has a solution around x0. That means it has a local solution. So option A is true. Now we are given the condition that xg is less than equal to 0. So we can place g as x days. So we are given x days is less than equal to 0. So to use this fact, we will differentiate x square. So d by dt x square equal to 2x x dash, and in place of x days we put gx because x days equal to gx, and it is given that x gx is less than equal to 0. So this derivative of x square will be less than equal to 0, which means x square t is decreasing function, and we can conclude that the solution xt is decreasing. Therefore the modulus of xt will be less than the initial point x0, which is x0. So mod xt is less than equal to x0 for any choice of x0 belongs to r. Therefore xt is bounded for any real number x0. So option D is correct because it says that all solutions are bounded. Also, since the solution is bounded, we have that it has no singularity, means for any finite time the solution does not go to infinity, or in other words it has no finite time blow up. So the solution exists for any choice of x0 belongs to r. That means it has a global solution on the interval 0 to infinity. So option B is correct also. Since there is no finite time blow up, option C is incorrect because option C states that there is a finite time blow up but solution is bounded, so this option will be incorrect option. This is a problem asked in 2020 exam, which is held on 26th of November. The problem is, let y0 is a positive number, z0 is a positive number, and alpha is greater than 1. And consider the following two differential equation. We are given two differential equation. One is marked as star and one is marked as double star. So for these two problems, a concept is defined that we say that the solution to a differential equation exists globally if it exists for all t. Which of the following statement is true? So we are given four statements and we have to pick which one is correct. So first option is both star and double star have global solution. Second option is none of star and double star have global solution. So we have to check the solution of the initial value problem star and double star, that star has a global solution or not and double star has a global solution or not. Third option is there exists a global solution for star and there exists a t such that limit t tends to t zt equal to plus infinity. In other words, the option C says that there exists a global solution for star but there does not exist a global solution for the initial value problem double star. And D option says that there exists a global solution for double star but there does not exist global solution for the initial value problem star. So we will calculate the solution, analyze it one by one. So for the initial value problem star, the initial value problem is given as dy by dt equal to y raised to the power alpha. We separate the variable, so dy by y raised to the power alpha equal to dt. On integration, we will get y raised to the power minus alpha plus 1 divided by minus alpha plus equal to t plus a constant e. We are given the condition that y0 equal to y0, we put t equal to 0 and in place of y we will put y0. So the value of the constant a will be y0 raised to the power 1 minus alpha divided by 1 minus alpha. When we plug in the constant here, we will get this equation and by multiplying it 1 minus alpha, we will get the solution. So basically I have written this in minus t alpha minus 1 because alpha is greater than 1, so alpha minus 1 will be greater than 0. So the solution of initial value problem star will be yt equal to y0 raised to the power 1 minus alpha minus t alpha minus 1 raised to the power minus 1 upon alpha minus 1. This is positive, so it is positive exponent, but there is negative. So when this becomes 0, the solution will tend to infinity. So if there exists a capital T greater than 0 such that y0 raised to the power 1 minus alpha minus t, we put here small t equal to capital T. When this will be 0, that is the capital T equal to y0 raised to the power 1 minus alpha divided by alpha minus 1, then limit t tends to capital T mod yt will be infinity. So the initial value problem star will not have a global solution. So option number 1 is incorrect and C is incorrect. Why? Because both the option states that the initial value problem star have global solution, which is not true. Let's check for initial value problem double star. So it is given that dz by dt equal to minus z raised to the power alpha with the condition z0 equal to z0. So by applying the procedure as we have applied for the initial value problem star, we will get the solution zt equal to z0 raised to the power 1 minus alpha plus t alpha minus 1. So this part is positive for any t. For any t, this will not equal to 0 or in fact it will be greater than 0. So as t tends to infinity, the solution this will tend to infinity and this negative exponent, so mod zt tends to 0. So limit mod zt will exist and we can say that zt defined for all t greater than 0. Hence the initial value problem double star has a global solution. So if we go to the example, so we have seen that option A is incorrect B will also be incorrect because B states that double star does not have a global solution, which is incorrect. Option C states that there exists a global solution for star, which is also incorrect. Option D is there exists a global solution for double star, correct, and there exists a capital T such that limit t tends to capital T yt equal to infinity. Hence, it is a correct option. The next problem is from the first paper of the year 2022. The problem is we are given two initial value ordinary differential equation of initial value. Problem 1 is dx by dt equal to x cube subject to the condition x0 equal to 1, and initial value problem B is dx by dt equal to x sin x square subject to the condition x0 equal to 2. This is asked that related to these ordinary differential equation, we have the following assertion. First is the solution to A blows up in finite time. Second is the solution to B blows up in finite time. So we have to examine which of two equation such solution like xt goes to infinity at t equal to t. So we have to check which of the two statement is correct or not. So let's begin. So first we consider the initial value problem A, dx by dt equal to x cube. By separation of variable method, we integrate this differential equation and condition is given as x0 equal to 1. By applying this condition, we will get c1 equal to minus 1 by 2. So the solution will be minus 1 upon 2x square equal to t minus 1 by 2. And we will get x square equal to 1 upon 1 minus 2t. When t tends to 1 by 2, the solution xt goes to infinity. Therefore, the solution to A blows up in finite time. At t tends to 1 by infinity, the mod xt will go to infinity. Therefore, the statement 1 is correct statement. Now we will consider the initial value problem B, dx by dt equal to x sin x square. Since we have that mod x sin x square is less than equal to mod x because sin x square's mod of sin x square is less than equal to 1. Therefore, mod x dash t equal to mod x sin x square is less than equal to mod x. We will apply the Gronwall's inequality, which states that if u dash t is less than equal to beta t ut for t greater than a, then ut is less than u0 exponential integral a to t beta s ds. If we take ut equal to mod xt and b a equal to 0 because the condition is given on t equal to 0 and beta as 1. Basically we are comparing these two. We will get u equal to xt and beta equal to 1 and a equal to 0. So by applying the Gronwall's inequality, we will get mod xt less than equal to mod x0 exponential integral 0 to t beta means 1 dot ds. So it will be 2 e exponential t. So mod xt is less than equal to 2 exponential t. If we take a finite time, that is t equal to capital T, then limit t tends to infinity, mod xt is less than equal to 2 e to the power t, which is less than infinity. So the solution of initial value problem B does not blow up in finite time. Therefore, the statement 2 is false. Hence, option B is the correct option. What is option B? So first option, if we analyze one by one, both are true, not. One is true, yes. Two is false, that is correct. So B option is correct. Next problem is the second paper of the year 2022. Consider the two following initial value problem. First is y dash x equal to y raised to the power 1 by 3 subject to the condition y0 equal to 0. And second problem is similar but the sign of right hand side is negative. Then we have to examine the uniqueness of the solution. So if we have to test that if one has unique solution or multiple solution. Similarly for second, it has unique or multiple solutions. Let's begin one by one. For the initial value problem second, y dash x equal to y raised to the power 1 by 3. We will separate the variable, and on integration we will get y raised to the power 2 by 3 divided by 2 by 3 x plus the constant of integration c1. It is given that y0 equal to 0, so we will get c1 equal to 0. Therefore, y raised to the power 2 by 3 equal to, if we multiply here, 2 by 3x. So yx equal to 2x by 3 raised to the power 3 by 2. For any c greater than equal to 0, we can define a solution of the given initial value problem as ycx equal to 0 when x is less than c, and if we replace x by x minus c, so 2 by 3 x minus c raised to the power 3 by 2, we can easily check that this satisfies the given initial value problem for all c greater than equal to 0. Therefore, the initial value problem 1 has infinitely many solutions. Now we will consider the initial value problem second. So it is given that y dash x equal to minus y raised to the power 1 by 3. On solving the equation, similarly as we solved the initial value problem first, yx will be obtained as yx equal to minus 2x by 3 raised to the power 3 by 2. If x is positive, then this will be negative. We can write it as 2x by 3 raised to the power 1 by 2 into minus 2x by 3. So this square root part, we must have that minus 2x by 3 is positive. So for x greater than 0, the solution yx is not defined. Also we have that the trivial solution yx is identically 0 is also a solution, because the initial value problems, the initial condition is given as y0 equal to 0, so it will satisfy the given initial value problem second, so it is a trivial solution. For positive x, there exists only a trivial solution, which is unique solution. So the initial value problem second has a unique solution. So let's analyze the example. 1 is uniquely solvable. No. 2 is uniquely, second problem is uniquely solvable. Yes, it is uniquely solvable. 1 has multiple solutions. Yes, it has infinitely many solutions. 2 has multiple solutions. No, it only has an identical solution, y x equal to 0. Alright, so option B and C are correct options. A similar problem was asked in CSIR NET 2023 June paper. The only difference is that here the exponent is 1 by 3. In that problem exponent was 1 by 2, and here also 1 by 2. So the exponent will not make any change to the solution. So the option B and C will be correct option for that problem also. 22 second paper of 2022. Okay, the problem is, let f defined from r square to r be continuous and satisfy these two conditions. If tx is positive, then f is negative. If tx is negative, f is positive. Consider the problem of solving the problem x dot equal to f of t comma x subject to the condition x0 equal to 0. Then which of the following is true? There are four options. There exists a unique local solution. There exists a local solution but may not be unique. There may not exist solution. If local solution exists, then it is unique. So we have to test the uniqueness and existence. So f is given that it is continuous function. So by Peano's theorem, the given initial value problem has at least one solution. So it has at least one solution. So option C will be incorrect. Now we consider that xt be a solution to the given initial value problem. Now we define yt equal to mod of xt. Then the derivative of y dash equal to the derivative of x multiplied by the, if we find the derivative of mod function, there will be multiplication of sine function sgn xt, which is defined as if x is positive, then Sgn is positive, or we can say it is +1, and -1 when x less than 0. So we arrive at the y dash t value. Now we will calculate that. We have to prove that the solution is unique, or a unique solution is given by x is identically 0 because of this initial condition. So we assume its contradictory fact that xt is not equal to 0. Now for t greater than 0, the Signum function st on multiplication with f of xt will be negative. Why? And it will become y dash t, and y dash t is less than equal to 0. So first we will see how it arrived. So t value is in 0 to epsilon. The sine function is defined as follow. If there is t is positive, we assume that if x is positive, then tx will be positive, and tx is positive, then f is negative, and sine function is positive by this. So by multiplication we will get negative sign. Similarly, when x is negative and tx will be negative because t is positive, so f will be positive but the sine function will be negative, so overall product will be less than equal to 0. So we arrive at that the condition y dash t less than equal to 0. Similarly, for t less than 0, the sine function multiplication with f of xt will be positive. Therefore y dash t is greater than equal to 0. So we calculated the derivative y dash t on the left and right side of the origin. Since y is continuous, so in the neighborhood of 0, y dash t will be 0. So yt will be identically equal to 0 because the condition y0 will be 0, and it conclude that xt is identically 0. Therefore, the given initial value problem has a unique solution, which is xt is identically 0. Hence, option A is true and option B is incorrect. Let's analyze the option. Option A is correct because there exists a unique local solution. Option B, there exists a solution but may not unique. No, it's incorrect because it is unique. There may not exist. Yes, there exists a unique solution, so this will be incorrect. B is incorrect, C is incorrect. Why the option D is incorrect? Because it's a single option problem, so only single option is correct. The option D is states that if local solution exists, then it's unique, but it's always exist. Therefore, more suitable option will be option A. Option D will be incorrect. Let's move to another problem which is asked in June 2023. The problem is let f belongs to C1R. C1R means the space of continuously differentiable function be bounded, so f is bounded. Let us consider the following initial value problem P. X dash t equal to f of xt for defined for t positive and x0 equal to 0. Then we have to examine the correct options. So first option is P has solution defined for all t. P has unique solution. P has infinite many solutions. So we are to test the existence of solution, whether it exists and it is unique or not. And the last option is the solution of P is R Lipschitz. So we have to check how many solution exist. It is defined for all t or it is Lipschitz. Since f is a C1 function, C1 means continuously differentiable function, so f is locally Lipschitz function. Since f is locally Lipschitz function, so the initial value problem has a unique solution around x equal to 0. Till now it has only the solution around x equal to 0, but it has a solution. Therefore, B option is correct and C option is incorrect. Okay. Now we have to check, is it defined for all t? So we have to use the condition that f is bounded. So there exists a positive real number m such that modulus of fx is less than equal to m. So fx is nothing but the x dash t, so mod x dash t is less than equal to m. Therefore the solution has no finite time blow up. Therefore the solution is defined for all t greater than equal to 0. Hence option A is true. Now we have to check that x is Lipschitz or not. So we consider the initial value problem dx by dt, and we write it as dx equal to f of xt. On integration from s to t, we get this. So it will be xt minus xs, and it will remain the same. We will use the fact that mod fx is less than equal to m. So by taking mod on both sides, it will be less than equal to m mod d tau. So we arrive at mod xt minus xx is less than equal to m mod t minus s. Therefore, xt, the solution of the initial value problem, is globally Lipschitz. Hence, the option D is correct. Consider the following problem: y dash equal to 1 minus y square raised to the power 10 cos y, subject to the condition y0 equal to 0. Let j be the maximal interval of existence and k be the range of the solution of the above problem. Then which of the following statements are true? We are given that j equal to r, or j equal to minus 1 to 1, k equal to minus 1 to 1, and k equal to close interval minus 1 to 1. So we have to find two things from here. One is the maximal interval of existence, and the second is the range of the solution. So it's a new kind of problem where we have to find the range of the solution. So it will be very exciting to discuss it, because this is the first time in CSIR NET exam a question on range of the solution is asked. So let's begin. First, we assume that f of ty equal to this. So we assume that function as f of ty, where f is a, since it is a polynomial function and a trigonometric function, so f is a continuously differentiable function on the whole real line. And also it has no finite time block because there is no negative exponent here. Therefore, the initial value problem dy by dt equal to f of ty subject to the condition y0 equal to 0 has a global solution. Therefore, the maximal interval of existence is r. So j will be r. So the first option is true. Now we will find the range of the solution. We cannot solve it directly, but we can use some techniques to determine the range of the solution. So first we will calculate the point of equilibrium. To calculate the point of equilibrium of this differential equation, we put the function as 0. So we will calculate the point of equilibrium. We put ft comma y equal to 0. So this is the function. We find the 0 of this function. So this part will be 0 when y equal to plus minus 1, and this part will be 0 when y equal to n pi plus pi by 2. So we have two equilibrium point plus minus 1. The solution yx slow downs when approaches to y equal to plus minus 1, because these are equilibrium point. When the solution reaches to either 1 or minus 1, the solution yt should be slow down. If we calculate y in between minus 1 to 1 open interval, then 1 minus y square is positive and cos y will also be positive. In both the cases, their product will be positive, hence y dash dy by dt will be positive. Therefore, the solution will become constant if it reaches to y equal to plus minus 1, because it is increasing function, so it will become constant to a point. So we can use this fact that y belongs to the open interval minus 1 to 1. What about exactly y equal to 1 or y equal to minus 1? So we let assume that at t equal to capital T, at a finite point of time, yt become 1. That is y capital T equal to 1. Now we assume that we will solve the differential equation, not explicitly, but by separation of variable we can write it as dt equal to dy by 1 minus y square raised to the power 10 cosine of phi. By integrating on the both side from the time interval 0 to capital T. So it becomes this. Since y0 equal to 0, and yt will be 1 because we have assumed that y capital T is 1. Now near y equal to 1, when y approaches from 0 to 1, near 1 we can assume that y equal to 1 minus epsilon, where epsilon is a very small positive number. So 1 minus y square will be 1 minus, we put y here, and it will be twice of epsilon minus epsilon square, which is approximately twice of epsilon, because epsilon is a very small number, so epsilon square will be negligible for very small epsilon value. So this part will be 1 upon 2 epsilon raised to the power 10. So it will go to infinity because epsilon raised to the power 10 is just near about 0. So this part goes to infinity near y equal to 1. So the time t will tend to infinity. But we have assumed that t is finite time, so yt cannot reach at 1 at finite time. Similarly, we can see that yt will not be equal to minus 1. Therefore, the range of the solution will be minus 1 to plus 1 in open interval. So k will be open interval minus 1 to 1. Hence option A and B are correct. Previously, we have shown that j will be r and k will be minus 1 to 1. This is incorrect option, and this will also incorrect because at any finite point of time the solution never reaches to plus 1 or minus 1. So the next problem is from same paper, December 2023. The problem is, consider the following initial value problem: y dash equal to y plus half of mod sin y square defined for x positive, x greater than 0, condition y 0 equal to minus 1. Then it is asked that which of the following statements are true. The statements are: there exists an alpha belongs to 0 to infinity such that limit x tends to alpha negative mod yx equal to infinity. Second option is yx exists on 0 to infinity and it is monotone. Third is yx exists on 0 to infinity but not bounded below. And last is exist but not bounded above. So we have to test the existence, monotonicity and boundedness of the solution. We will solve it by using the comparison theorem. So first it is given that the function is y plus half of mod sin y square. We know that the sin value is in between minus 1 to 1, so mod of sin function is less than equal to 1. Therefore half of mod is less than equal to half. Therefore y dash, which is half y plus half of sin y square, which will be less than y plus 1 by 2. Also y dash is greater than y because y dash is y plus this positive part, so y dash is always bigger than y. So we have that the value of y dash lies in between y and y plus 1 by 2. So we will use two comparison, first for this part and second for this part. Alright, for the first part we define z dash equal to z such that with the same condition for the given initial value problem. The condition is y0 equal to minus 1, we will define z0 equal to minus 1. We will solve this problem by using the separation of variable method, and by applying the condition we will get the solution zx equal to minus exponential x. Since it is given that y dash greater than equal to y and we have this comparison theorem, if y dash equal to f of xy and u dash x equal to g of u with the condition that f of xy is greater than equal to g of y subject to the same condition as y, then yx is greater than ux for all x in the common interval. So we have to use this part, fxy greater than equal to zy, then yx will be greater than equal to ux. Here we have considered that y dash is greater than y, y dash is f of xy. So by comparison theorem, we conclude that yx will be greater than equal to minus e to the power x. For the second comparison, we define a function like this. So omega dash equal to omega plus 1 by 2, where omega 0 equal to minus 1 by 2. This is a linear differential equation of first order. By solving and using the condition, we arrive at the solution omega x equal to minus 1 by 2 exponential x minus 1 by 2. By again comparison theorem, but this time y dash is less than y plus 1 by 2. So yx will be less than equal to this omega x, which is equation 2. By combining both the equation, we arrive at that yx lies in between minus exponential x and minus 1 by 2 exponential x minus 1 by 2. So yx stays between two smooth function. Exponential function is a smooth function. So it exists for all x greater than 0. It will become infinity when x tends to infinity because there is no finite time block. So option A is incorrect. Option A suggests that there exists an alpha such that y tends to infinity, but there is no finite alpha such that solution goes to infinity. So option A is incorrect. Now it is given that yx greater than equal to exponential minus x. So yx tends to minus infinity as x goes to infinity. Therefore yx is not bounded below. So option C is correct. C option is yx exists, alright, and bounded below. It is not bounded below. So yx is not bounded below. Option C is correct. Now for positive x, y dash x is less than y plus 1 by 2. At x equal to 0, y dash 0 is less than equal to y0 plus 1 by 2. And y0 is minus 1. So y dash 0 is less than equal to minus 1 by 2, which is negative. So y dash 0 is negative. Therefore the solution began to decrease at x equal to 0. If y become more negative, then the term y dominate the term half of sine y square, and hence this combined term will become negative. Therefore y dash x is less than 0 for all x positive. So we can say that yx is monotonically decreasing function.
So yx decreases from minus 1, that is from its initial value, to minus infinity, that is yx is bounded above by minus 1. Okay, so yx is monotonically decreasing but it is bounded above, and option D says that it is not bounded above but it is bounded above. So option D will be incorrect option. Option A is incorrect. B and C are correct options for this problem. The next problem is from June 2024 paper. The problem is, consider the initial value problem y dash x equal to sine yx divided by 1 plus y raised to the power 4, defined for all x belongs to R and subject to the condition y0 equal to y0. Then which of the following statements are true? There is a positive y0 such that the solution for the initial value problem is unbounded. There is a negative y0 such that the solution for the initial value problem is bounded. For every y0 belongs to R, every solution of the initial value problem is bounded. And D option is, for y0 belongs to R, there is a solution of the initial value problem for all x belongs to R. So first we will see about the initial value problem. So y dash x equal to sine y 1 plus y raised to the power 4 subject to the condition y0 equal to y0. We assume this function as f of xy. Since sine y is less than equal to 1, modulus of sine y, so modulus of f of xy is less than equal to 1 upon 1 plus y raised to the power 4. This part is positive, so the overall will be less than equal to 1. So y dash x is less than equal to 1. Therefore we conclude that there is no finite time blow up in the solution yx. Therefore yx is bounded for all y0 belongs to R. Therefore option C is correct. What is C? C option is that for all y0 belongs to R, every solution is bounded. there is a negative y0 such that solution is bounded? Yes, it is bounded for all y0. Either it is positive, it is negative. So option B is correct, option C is correct, but option A is incorrect because it states that it is unbounded. No, it's bounded. Now, since f of xy is continuous, so by Picard-Lindelof theorem, the initial value problem has a solution in an interval around x equal to 0. Now we will calculate the modulus of del f upon del y. So by differentiating the f with respect to the variable y, we will get this, and by calculating the modulus, because mod of cos y less than equal to 1, so we will break it down to this. Now we will solve this. What is this? Y raised to the power 4 is always greater than y raised to the power 3. So by adding 1, it will not change the inequality, and we will get y raised to the power 3, 1 plus y raised to the power 4 is less than 1. By multiplying it 4, and we can see that 4 y mod y raised to the power 3 upon 1 plus square is less than 4 upon 1 plus y raised to the power 4. We will plug in this value here, so we will get mod del f upon del y is less than 5 upon 1 plus y raised to the power 4. So f is globally Lipschitz function. So the given initial value problem has a unique solution for all x belongs to R. Therefore the option D is correct. So we can say that B, C and D, these three options are correct, and A is incorrect option.
Next problem is from the paper June 2024. The problem is, consider the initial value problem y dash x equal to square root of mod yx plus epsilon subject to the condition y0 equal to y0. Then there are two statements. First statement is that there exists an epsilon positive such that for all y0 belongs to R, the initial value problem has more than one solution. Second problem is, there is a y0 belongs to R such that for all epsilon positive, the initial value problem has more than one solution. So both the statements say that there exists more than one solution. If there we fix the epsilon, then for all y0 there is infinitely many solutions, and similarly if we fix a y0, then for all epsilon greater than 0 there exists infinitely many solutions. So we have to test which of the statement is correct or not. So let's begin. So the given initial value problem is this: y dash equal to square root of mod y plus epsilon subject to the condition y0 equal to y0. This initial value problem has multiple solutions if the function, if we consider it as f, is not locally Lipschitz. If it's Lipschitz, then there will be unique solution. When will it happen? If the function fxy fails to be locally Lipschitz, if this modulus value is equal to 0. Therefore, we want to calculate what happen when x equal to 0. So at x equal to 0, y is y0. So y0 plus epsilon equal to 0. Only this condition will imply that the given initial value problem has multiple solutions. So y0 equal to minus epsilon or epsilon equal to minus y0. So for a given epsilon, the only value of y where the initial value problem has multiple solution is y0 equal to minus epsilon. Therefore S1 is false. Why it's false? Because S1 states that for a given epsilon greater than 0, for all y0 there has multiple solution, but only for this particular value there is multiple solution. Rest of the values there is a unique solution. Similarly, for a given y0, the initial value problem has multiple solutions if we fix epsilon as minus y0. The rest of, for the all rest of the epsilon, there is only a unique solution. Therefore, the statement S2 is also false. So, the option D is correct option.
Now the next problem is from December 2024 paper, which is held on 28th February 2025. So for B belongs to R, let yb equal to ybx be the unique solution of the initial value problem this, subject to the condition y0 equal to b. So for each b there exists a solution, and which is denoted by yb. Defined on its maximum interval of existence denoted by ib, then which of the following statement are true? So option first is there exists an alpha which is positive such that for every b belongs to R with b greater than alpha, the solution is bounded above on ib. Similarly, yb is bounded below on ib. There exists an alpha belongs to minus infinity to 0, that is alpha negative, such that for every b with b less than alpha, for a negative b, the solution yb is bounded above on ib and bounded below on ib. So we have to check the boundedness dependent on the value of b. Let's start the solution. Now consider the initial value problem dy by dx equal to f of y, where y0 equal to b is the condition and f of y equal to this polynomial function. Okay, so polynomial function, therefore its Lipschitz is continuous. The solution of the given initial value problem is unique. Alright, and the maximum interval of existence ends exactly when mod yx tends to infinity in finite time. When yx tends to infinity at x equal to some value, then the interval will at end x0. Similarly, if minus infinity at x0 dash, okay, so the maximal interval of existence ends when mod yx tends to infinity in a finite time. Now we will consider two cases, large value of y and large value of negative y. So first we will consider the large value of y greater than 0. So f of y is polynomial function for y greater than 0, f of x y, f of y will be positive. So y dash x is fy, so y dash x will be positive. Yx is strictly increasing. So yx will be greater than equal to b because y0 equal to b is the initial point. Alright, if b is positive, then the solution is bounded below by b but not bounded above, because the solution will start from the point b and then keep on increasing. So it will be bounded below. Therefore A option is not correct, but B option is correct. A option says that it is bounded above, but B option says that it is bounded below. Alright, next consider for large negative values of y. So fy tends to infinity in finite time and y dash x will be negative. So yx is strictly decreasing. So yx will be less than equal to b, which is less than alpha. So for a negative value of alpha, the solution yx is bounded above by b or alpha say, but not bounded below. So the option C will be correct and D is incorrect option.
The next problem is from the paper December 2024, which is held on 2 March 2025. So the initial value problem is given as dy by dx equal to square root mod x minus 1 multiplied by sin y, subject to the condition y0 equal to 1. And we have to check that option A unique solution on R, B infinitely many solution on the interval minus 2 to 2, a unique solution and its maximum interval of existence is minus infinity to 1, and option D is no solution on the interval minus 2 to plus 2. Let's begin. The given initial value problem is given as dy by dx equal to square root mod x minus 1 sin y, subject to condition y0 equal to 1. Let this as a function f of xy, which is a continuous function on R cross R. Also, the derivative of f with respect to y will be mod x minus 1, the derivative of sin y will be cos phi, which is also continuous. So f of xy is globally Lipschitz and the solution of the given initial value problem exists uniquely on the R. It has global solution and unique global solution. So the maximal interval of existence is R, hence option E is correct. So a unique solution is R. Infinitely many solutions? No. Unique solution? Yes, but maximal interval of existences are not this, so it is incorrect. No solution? No, it's not possible. So only option E is correct option. The next problem is from the recent paper from CSIR NET June 2025. The problem is that let D equal to, as domain is defined, xy belongs to R square such that x is in between -1 to 1 and y is in between -1 to 1, and a function is defined from D to R be the function defined by this f of xy equal to 1 plus square root of y plus, where y positive means the maximum value from y and 0. Let's define the initial value problem dy by dx equal to f of xy subject to the condition y0 equal to 0. Then we have to check which of the following statements are true. First option is f is Lipschitz continuous function on D. Second option is f is not a Lipschitz continuous function. And third is the initial value problem has at least one solution and initial value problem has no solution. So let's check it. The function is given as 1 plus square root y positive. If we define for y positive, it will be 1 plus square root of y when y is less than equal to 0. So the maximum value will be 0. So it becomes 0 and function will be 1, which is a continuous function. The limit, if we check the limit, will be 1 at the break-even point y equal to 0. Alright, the given initial value problem has at least one solution y by Peano's theorem. If f of xy is continuous, then the initial value problem has at least one solution. So option C is correct, but D is incorrect. What is C? At least one solution. Okay. And D, no solution. No, it's incorrect. Now, in the neighborhood of y equal to 0, let's check for y positive. Del f upon del y equal to 1 upon 2 root y, which tends to infinity as y tends to 0 positive limit. If f is not this means it is not bounded. If it is not bounded, then f is not Lipschitz continuous. Therefore, option A is incorrect and B is correct. So option A is f is Lipschitz continuous. No, f is not Lipschitz continuous. Okay, so B is correct option. So we have two correct options, B and C. Alright, this is it. We have discussed all the problems on existence, uniqueness and solution blow up asked in CSIR NET exam from the year 2011 to the latest 2025. This video will definitely help you in the upcoming CSIR NET exam of December 2025, as one or two problems will be asked from this topic, and more importantly it require only a few concepts which are very easy to apply. In case any problem is missing in the discussion which is different than the ones we have done here, feel free to comment or write it in my Telegram channel. The notes will be uploaded on my Telegram channel, whose link is in the description box. All the best for the exam and share it with your friends who are preparing and want sure success in the exam. Thank you for your attention, for watching it till the end.